let's have a look at the newly established transversal magnetization vector. This moves in phase with the precessing protons. The new magnetic vector comes towards you, goes away from you, comes again towards you, and so on. And this is important. The magnetic vector, by constantly moving, constantly changing, induces an electric current. We've talked about the opposite already. The moving electrical charge of the proton, the electric current, induces the proton's magnetic field. This also is true the other way round. A moving magnetic field causes an electric current, for example, in an antenna. And this electric current, induced by the moving magnetic field, is the MRI signal. As the transversal magnetic vector moves around with the precessing protons, it moves with the precession frequency. The resulting MR signal, therefore, also has the precession frequency. But how can we make a picture out of this electric current, which actually is our MR signal? For this, we have to know where in the body the signal came from. How can we know that? The trick is really quite simple. We do not put the patient into a magnetic field which has the same strength all over the section of the patient which we want to examine. Instead, we take a magnetic field which has a different strength at each point of the patient's cross-section. What does this do? We have heard that the precession frequency of a proton depends on the strength of the magnetic field, as the frequency of a violin string depends on the strength with which you pull it. If this strength differs from point to point in the patient, then protons in different places precess with different frequencies. And as they precess with different frequencies, the resulting MR signal from different locations also has a different frequency. And by the frequency, we can assign a signal to a certain location.